Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 5 on the area of a circle. So you've studied the area of a circle before, you probably even vaguely remember the formula for the area of a circle. Maybe you remember it exactly. Anyhow, let's jump right into it and get into this discussion. The area formula for a circle. The area formulas for rectangles, parallelograms, and triangles should all make sense from the perspective of multiplication and counting squares, unit squares, that lie within the figure. We also want to be able to measure the area that lies within a circle. You've learned the area formula for a circle in previous courses, so let's review that right now. The area of a circle. The area that lies within a circle, whose radius is given by r, is area equals pi times r squared. All right, now I just wanted to mention something. In our next lesson, we're going to look a little bit at where this formula comes from, and yet again, we're going to discover the number pi with the help of some trigonometry. All right, but we want to give nod to the fact that we haven't really proven this formula, so to speak, and it's also a little bit strange. The idea that we would measure how many little squares we can fit inside of a circle is strange, and maybe that's even why the pi shows up. Regardless, for the rest of the period, we're just going to be using this particular formula to solve and model a variety of situations. So let's take a look at exercise number 1. Given a circle with the equation x plus 2 squared plus y minus 7 squared equals 36, do the following. Letter A, identify the center and the radius of the circle. All right, well, take a moment. We've obviously done this before, right? We've actually, just done this recently in our last unit. So see if you can identify the center and the radius of this circle. All right, really quickly, I gotta just pop out of here fast and get my pen all set up. Now, what we know, right, is that we can see the center of the circle by looking at the coordinates or the numbers that are being added and subtracted to x and y, all right? Because it's x plus 2 and y minus 7, what we hopefully remember from the last unit is that the center of the circle is going to be at -2, 7. Now, that doesn't really help us very much with the area that we're going to get to in letter B. For that, we need to know the radius. And what I hope we remember from the last unit is that the 36 represents the square of the radius, right? So the radius squared is equal to 36, and therefore the radius is the square root of 36, or just 6. So we've got a center at -2, 7 and a radius of 6. Letter B. Give the area of the circle both in terms of pi and to the nearest hundredth. Now, we don't have any kind of units here like centimeters or inches or anything like that, so we can't say they're centimeters squared or inches squared or anything like that, so we're just going to leave it without units. But we know that the area formula is pi times r squared. We know that r is 6, so we're going to get pi times 36. We don't tend to leave it like that ever. We kind of treat pi as if it's like the variable x or something like that. So we're just going to leave that as 36 pi. Now that's what it means to give the area in terms of pi. In other words, our area is exactly 36 times pi. But in practical scenarios, you almost always want to know areas or lengths or volumes or whatever rounded to a particular degree of accuracy, in this case to the nearest hundredth, and that's easy enough then to just type in 36 pi on our calculator, right? Hit enter. It does everything for us, so our area is going to be 113, a little bit irritating on the rounding, 0.10. All right. Now again, it's not unusual that you have to have your area in terms of pi, and very often we're going to want our area in terms of pi maybe until the end, and then we'll let our calculator kind of do its magic, round, etc. All right, speaking of our calculator, let's get rid of that and keep working on this. Now, circles and semicircles are often added to polygons to create more complex shapes, and let's look at that scenario in exercise number 2. A shape is constructed from a rectangle whose length is 10 inches and whose width is 8 inches, along with a semicircle attached at one end. Which of the following is the total area of the shape in square inches? Now notice, right, each one of these answers involves pi. So the area in this case, is given as an exact answer in terms of pi. What I'd like you to do now is pause the video and see if you can figure out which is the correct choice. All right, well, I think that you've probably seen problems similar to this. We want to add the area of the rectangle to the area of the semicircle. That's going to be easy enough, right? The area of the rectangle is going to be 8 times 10, which is going to be 80. Now, the area of the semicircle is going to be 1/2 times pi times r squared. Of course, it has to be 1/2 because it's half of a circle. The key here is that our radius is equal to 4, right? So the area of our semicircle is going to be 1/2 times pi times 4 squared. That's going to be 1/2 times pi times 16. And always keep in mind that when you have the product of three numbers, right, pi times 1/2 times pi times 16, we can do that product in any order we want. So I'm going to do 1/2 times 16, and I'm going to get 8. And so the area is 8 pi. All right, so what is the area of my overall figure? Well, obviously, those two areas, right, add together, and we're going to get 80 plus 8 pi. Now, the question is, should I circle choice 1, 88 pi, or should I circle choice 4, 80 plus 8 pi? Now, maybe it's obvious, because this says 80 plus 8 pi, that we should circle choice 4. And in fact, choice 4 is correct. The real issue, though, that I want to make sure you understand, right? Because if this isn't a multiple choice question, if this is free response and they say, leave your area in terms of pi, you can't make it into 88 pi. The only way you could do that is if it was 80 pi plus 8 pi, right? There is no pi attached to the 80, right? Think about it as x. If you had 80 plus 8x, you couldn't make it 88x, right? You couldn't do that. And just the same, if I have 80 plus 8 times pi, right, order of operations, that 8 times pi is its own term and cannot be combined with the 80. All right, so that's just important. All right, let's take a look at one that's a little more challenging. Exercise number 3. The radius of circle M below is 13 centimeters. Diameter AC is drawn and point B is located such that BC equals 24 centimeters. Determine the area of the shaded region in terms of pi and accurate to the nearest square centimeter. Ooh, all right. Well, here we've got kind of almost the opposite scenario as what we had in exercise 2. Here we have a subtractive problem instead of an additive problem, right? We want to figure out the area of the entire circle. That's going to be easy enough. And then we want to subtract off the area of the triangle, right? So let's kind of write that down as our strategy. The area that's shaded is going to be the area of the circle, the area of the circle minus the area of the triangle. Okay, the area of the circle minus the area of the triangle. Let's go ahead and figure out the area of the circle right away, just get that done with, and then we'll talk about the harder task, which is figuring out the area of the triangle. The area of the circle, right, is going to be pi r squared. They said that the radius of the circle is 13, so that's easy enough. 13 squared is 169. So the area of the circle is 169 pi, and I'm not going to figure out what that is in terms of a decimal because I want my final answer in terms of pi and accurate to the nearest square centimeter, so we'll let our calculator do its magic when it's time. Now we have to figure out the area of the triangle, and that's a little bit tougher. I'd like you to pause the video right now and really think about everything you know in this problem, including maybe extending your knowledge back to our last unit. That's going to be helpful and important to be able to figure out the area of that triangle. Pause the video now and think about this for a bit. All right, well, what do we know? We know that BC is equal to 24 centimeters. I'll write that down right here. We also know that because the radius is equal to 13 centimeters, that diameter is equal to 26 centimeters. Now, I would hope that nobody in here would think that we could just do 24 times 26 and divide by 2. That would just be weird, right? But here's the key. This is a triangle that is inscribed in a semicircle. And because it's a triangle inscribed in a semicircle, this must be a 90-degree angle, right? That arc, AC, is a semicircular arc, so it's 180 degrees, which means angle B is half of that, which is 90. Now, since this is a right triangle, if I knew the length of AB, I could just multiply the length of AB times the length of BC and divide by 2. But that means I have to figure out the length of AB first, and for that, we need to use the Pythagorean theorem, right? So pause the video now, see if you can figure out the length of AB using the Pythagorean theorem, then see if you can come up with the area of the right triangle, and then see if you can come up with the final answer. Pause the video now and take one more shot at this. All right, well, I'll call that, let's say, A, right? And I'm going to have A squared plus 24 squared is equal to 26 squared. I don't know any of those off the top of my head, so let's get the calculator out. 24 squared is 576. 26 squared is 676. Subtract them and we'll get A squared is equal to 100, which means A must be equal to 10. All right, which is great, right? This is equal to 10. And now I can say that the area of my triangle is 1/2 of 10 times 24. And that means the area of my triangle is going to be 1/2 of 240, or 120. And now I have everything I need to finish this problem out, right? The area that's shaded is going to be the area of my circle. So the area that's shaded is going to be the area of my circle, which was 169 pi, minus the area of my triangle, which is 120. And that's what the answer is in terms of pi. So they asked us to do two things. They wanted to have our answer in terms of pi, and that's this. And then they wanted the answer to the nearest square centimeter, which we'll get right now. And it'll be as easy as this, right? We're going to do 169 pi minus 120, enter. And that means that the area that's shaded is equal to 411 square centimeters. And again, let's give it up to the fact that in any kind of practical situation, right, any kind of real world situation, eventually you're going to want this answer. This answer is great to have because it's exact, okay? Meaning that no matter what, I can figure out how accurate I want my answer by plugging this into the calculator and then taking off however many decimal places I want or need, let's say. But if they then say, hey, to the nearest square centimeter is fine, there we have it. Okay? So, let's keep going. All right, now, we have all sorts of sophisticated techniques that can come in right now and come into play. Let's take a look at exercise number 4. A shape is being designed that is a combination of an isosceles triangle with a semicircle whose diameter is the base of the triangle. The isosceles triangle has legs that are 10 inches long and a vertex angle that measures 44 degrees. Letter A, what is the area of the isosceles triangle to the nearest hundredth? All right, so you probably know where we're going with this already. I want to come up with the area of this overall shape, okay? And the first thing we're going to do is come up with the area of this isosceles triangle to the nearest hundredth. Why don't you pause the video and go ahead and figure out what that is? All right, well, keep in mind, anytime we've got a triangle where we know two of the side lengths and we know the angle in between them, we can always use the area formula for a triangle that depends on trigonometry. The whole area equals 1/2 a times b times the sine of c, or in this case, the area is equal to 1/2 of 10 times 10 times the sine of 44 degrees. Let's figure out what that area is to the nearest hundredth. 0.5 times 10 times 10 times the sine, make sure I'm in degree mode, I am, of 44 degrees. Yep, just wanted to make sure that was 44. and that's going to be 34.73 square inches. All right, so the area of my isosceles triangle, 34.73 square inches. Now, we're going to eventually want the area of that semicircle. That's going to be 1/2 pi r squared, just as it was a couple problems ago. But in order to do that, we've got to do letter B first. Let's take a look. Determine the radius of the semicircle to the nearest hundredth. All right, so I want to figure out the radius of the semicircle. I want to know this length, right? Pause the video now and see if you can figure out how to do that. Well, anytime we have an isosceles triangle, right, and we know the leg lengths or the base length, and we know one of the angles, either the vertex angle or either of the two base angles, we can figure out everything else by carving this isosceles triangle into two congruent right triangles and then using right triangle trig. In other words, what I'm going to do is I'm literally going to drop an altitude like this, right? That's going to give me a triangle that looks something like this. This is now 22 degrees. This is 10 inches. And actually, my radius is that, right? Now I've got my angle. I've got the side opposite the angle. That's what I want to know. And I've got the hypotenuse. Whenever I have the angle, the side opposite, and the hypotenuse, we're talking about the sine ratio. So the sine of 22 degrees is going to be equal to r divided by 10, which means r is 10 times the sine of 22 degrees. Let's figure out what that is using our calculator. All right, 10 times the sine of 22, and we're going to get r is 3.75 inches. All right, letter C. Using A and B, determine the overall area of the figure to the nearest square inch. All right, lovely. I like this one. We don't have to worry about getting it in an exact form of pi or anything like that. They've also given us permission to use both this answer in that rounded form and this answer in its rounded form to calculate our final answer. Pause the video now and see if you can figure those out. All right, well, let's do it all at once, okay? We know that the overall area is going to be 34.73, right? That's the area of that isosceles triangle, plus now 1/2 times pi times my radius squared, all right? And I can put all of that into my calculator all at once, right? That first thing is just the area of the isosceles triangle, 34.73 plus 1/2 times pi. Don't forget the pi. That is the most common mistake students will make in problems that involve pi, is actually forgetting it, which I find a little bit ironic. We hit enter, and we wanted the area of the overall figure to the nearest square inch, so that's going to be 57 square inches. Right? And I don't ever need to have it exact in terms of pi. There we go. All right, let's do one last problem. All right, now a lot of what you are asked to do in terms of geometric measurement and modeling is to look at real-world objects like this pond and somehow use the geometry that you know to model it, even if it's not an exact shape. Let's see how that might be done in a scenario like exercise number 5. A pond has a roughly circular shape with a center at point C. Landowners would like an estimate for the area of the pond. Use your ruler, compass, and the scale shown to calculate a reasonable range of areas for the pond. Show how you arrived at your answer. All right, so imagine that you're, a water resource engineer or something like that, right? We want to get a range, okay, a range of areas that are reasonable for this pond. And it's roughly circular, right? But it's not circular, okay? Now, what would be cool is to find the largest circle that fits within the pond and find the smallest circle that goes all the way around the pond, right? And those two circles should then give us a good sense for the area of the pond. Now, it might actually be a little bit easier for you than me because you've got a piece of paper there, you got the pond. The idea is that we're working off of a map, which is why we have a map scale here that's being covered up by all sorts of things. Let's get our calculator out of the way and things like that. So, I might look at this thing and I might go, okay, well, if I take my compass out and I put the point right there, I don't know, where is going to be the sort of like the smallest radius? And it's probably going to be maybe right around here. Again, it's a little bit tricky to note exactly, but maybe the smallest radius about there. And again, if you've got your compass, you can actually play around with this a little bit, but I think I'm gonna try to draw that circle. Yeah, that's not bad. Actually, that's pretty good, if I do say so myself. Right, so that particular circle just fits inside of the pond, right? And maybe I'll go ahead and measure what its radius is. Now remember, this is on a particular map, so if I take my ruler out and I measure that radius, okay, what I'm seeing is a radius that's right around 4.4 centimeters. All right, that's about 4.4 centimeters. Maybe I'll even kind of draw this in. All right, so that radius out to there, 4.4 centimeters, and we'll eventually figure out what the true radius is by using our scale factor. But that's going to be sort of the smallest area that the pond could obviously be in. Obviously, the area of the pond is more than that because there's pond outside of it. But now maybe what we want to do is we want to get a bounding circle on the outside. Pause the video now and see if you can get a circle that just fits around the pond, right? So what you really want to do is find the farthest point from C, and it's probably like one of these guys, in here, one of these things that kind of bumps outward. Pause the video now and see if you can surround the pond with a circle and then figure out the radius of that particular circle. All right, well, again, it's a little bit tricky. I'm kind of looking at it. I'm thinking maybe it's this one here. And for you, it probably is a little bit easier because you can kind of play around with it some, but I'm thinking that is probably the best. Let me just sort of rotate this thing around. Yeah, I don't particularly see any more that are farther away than that one, so let me do that. And yeah, that looks pretty good. I think I maybe should have brought it up to here. It's a little bit tricky, so maybe I'll kind of measure that distance. All right, let me take a look and see how far this one is away. And that's about 5.2 out to there. Whoops. That's 5.2 centimeters, right? So whatever the actual area of the pond is, and that would be hard to figure out without some more sophisticated GPS techniques, but whatever the area of the pond is, it's going to have to be within the interval of the area of this circle and this circle. Now again, that 4.4 centimeters and that 5.2 centimeters aren't the actual radii, right? The actual radii we need to figure out from this conversion that says 1 centimeter on the map is equal to 1.5 meters in the real world. So let's actually figure out the radius, the small radius, right? The small radius is going to actually be 4.4 centimeters times 1.5 meters per 1 centimeter. So let's figure that one out. Okay, let me clear all this chaff out of the way. All right, so we've got 4.4 times 1.5. Looks like 6.6 meters. All right, and then my larger radius is going to be 5.2 centimeters times 1.5 meters per 1 centimeter. And let's figure out that, 5.2 times 1.5. and that's going to be 7.8 meters. Now again, there's all sorts of little bits of inaccuracy that are built into this, right? We know that the area of the pond is going to be somewhere in between this, but there's some error in these measurements. Of course, then when we convert them over, there's errors in these measurements, etc. But now what we want to do is we want to just figure out what the area of the small is and the area of the large, okay? So in fact, why don't you pause the video now and see if you can make a final statement, something to the effect of the area of the pond is between this and this. That's what a range is. Pause the video now and see what you have. All right, so let's do it. Get rid of that all the way. Whoops. Let's go back up here. So the smallest that the area of the pond could possibly be is pi times 6.6 squared. And let's bring that out. Here we go. We'll go pi times 6.6 squared. And I'm going to say that's 137 square meters. And the area of the larger circle is going to be pi times 7.8 squared. So pi times 7.8 squared, and that's 191 square meters. So we can say, right, I can't really move that scale anymore. Maybe I can. Nope. The pond will have an area between 137 square meters and 191 square meters, which, by the way, is quite a large range, right? Now, if you were an engineer or somebody like that, you might say, well, if I really had to then take a best guess estimate for the area of the pond, maybe I would take these two areas and I would average them, something like that. And that would give me a really good sense for how large this pond is. But if I really want to just be honest about the uncertainty of my measurement, right, then I would be able to say, hey, look, I don't know what the exact area is, but I know it's not less than 137, and I know it's not more than 191. All right, let's wrap this up. Now, in reality, we didn't do too much today that was new, right? You knew the area formula of a circle. You certainly knew how to add areas of circles to other things and subtract areas from other things, all right? So all we were really doing today is using the more sophisticated tools that we've developed in this course, such as the Pythagorean theorem, circle theorems, the geometry, right, like the geometry of the circle, the area formula for a triangle that depends on trig. All of those things came into play while we were dealing with the area formulas of a circle that wouldn't have in previous courses, all right? So you certainly have to do more than what you would have done in 8th grade or 7th grade with the area of a circle. But at the end of the day, you do need to know that the space inside of a circle is calculated by pi times its radius squared. And that's very, very important to know that and distinguish it between obviously the circumference formula of a circle, which is simply pi times its diameter or 2 pi times its radius. Now in our next lesson, we'll explore a little bit about why the area formula for a circle is pi r squared. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.